consent video recording. I have to manually switch on the camera and mic. Okay. Maybe Sai and Suman. Yes, and Salah and Shabir. Okay. Okay, let's start the session. Shabir and Salah, please switch on your video camera. Okay, let's start our session. Okay, good evening, guys. Hope everyone has a very good day. So today's our session is special topic discussion. So we are planning to have each one of us will be presenting a topic and within 10 or 15 minutes. And after that, we will move on to a Q&A session. In that time, the other team members will be asking any questions if they need any clarification in that particular topic. So we are planned to have first mechanical team will be presenting the session that will be starting with Salah, and then we will move on to Taslim. And after mechanical, we will be moving to instrumentation team, and then electrical, and last will be the safety. So without further delay, we will move on to the mechanical session. Salah, please start with your session.
Hi, thank you, Riaz, for giving this opportunity to give a brief description about my topic. Here I would like to give some description to detailing about the steam generator in a nuclear power plant. So let me share my one slide to you. I hope you can see my window, right?
Yes, Salah.
Okay, so here regarding the steam generator, I would like to give some details. So first one, I want to give you what is a steam generator, and second function of a steam generator in a nuclear power plant, especially in pressurized water reactor, and steam generator design and working of steam generators, importance of the steam generator in the reactor operation, and common issues in the steam generators, and steam generator maintenance and inspection. So let me go to first topic, that what is a steam generator? Actually, the steam generator is a type of heat exchangers which transfer from one fluid to another fluid. So here in the nuclear power plants, it acts as an interface between the primary circuit and secondary circuit. So here the heat transfer from the primary circuit and the steam producers in the secondary circuit. So then using this steam, turbine using the steam, this which drives the steam turbine generators, then it go for the electricity production in a nuclear power plant. So typically we can say like a steam generator is a kind of heat exchanger, and it is a very critical component in a pressurized water reactor nuclear power plants. So let's go to next function of a steam generator. What is the function of a steam generator? So mainly we can say a function of steam generator. As I said earlier, what is the steam generator? So main function is the heat transfer. The transfer heat from the high pressure, high temperature primary coolant, that is from the reactor core, and to the secondary side without mixing the two fluids. This is the main function of the steam generator. Then next function we can say like which produces the steam production. Means converts the feed water into dry saturated steam that powers the steam turbine. And the steam generator also acts as a barrier between the radioactive primary system and a non-radioactive secondary system. We know the primary system, which includes the many radioactive materials. So steam generators like act as a barrier between two systems, means secondary and primary, and preventing the contamination as well. And the last function, not last, but we can say using the steam generator, we control the flow also, coolant flow also. So for better performance, for better efficiency of the plant, so we have to control the coolant flow throughout the process. So steam generator ensures the stable flow dynamics in both the primary and secondary circuits. So then we can maintain the proper output and with the safety. So these are the main four functions we can say, like heat transfer and steam production, and it acts as a pressure boundary between the primary system and the secondary system. And the last we can say like it function like a coolant flow regulation also. Then the next topic, what is steam generator design? So we can say like two sides, primary side and secondary side. The primary side means we can also call it as like a hot side. The hot reactor coolant means from the reactor core. That is would be about 310 degrees Celsius. It will enter into the steam generator through the primary inlet. I will show you the one sectional view of the steam generator. Then I will come back. Then I will come back to this design back. I hope you can see the one section view of the steam generator.
Yes, yes, you can see.
So this is the sectional view of a. I think you can see the view, right?
Yes, yes.
Okay. So this is the one sectional view of a P1000 steam generator. So here, these are the YouTube heat exchangers, which is the YouTubes are here, and here we can divide it like two integral sections. That is the evaporator section and the steam drum section. The steam drum, this steam drum sections consist of the moisture separating equipment. So this area we can call it as like that, which removes the most the entrained water from the steam. So you can just view the steam sectional view, and let me tell you, these are the feed
Can you
water
please
nozzles.
enlarge the view?
Yeah, okay, sure.
Okay.
So, okay. So these are the primary inlet nozzle and outlet nozzles are here. Through this, the primary coolant, reactor coolant will enter and it will go outside through the primary outlet. And the feed water also, feed water nozzles are here. The feed water will enter and the feed water will also fill in this area and the heat will transfer from the reactor coolant and the steam will produce. Then it will go to, steam goes to the turbine island. So this is the sectional view. So let me come back to the more detail about the design. So let me tell you then that we can divide it like a primary side and secondary side. The primary side, the reactor coolant is entering to the steam generator through the primary inlet, what I shown in the section view. The temperature of that the reactor coolant would be about 310 degrees Celsius. Then it circulates through about there would be thousands of YouTubes like means we are using the YouTube heat exchangers. That is like inverter U shape. And after heat transfer, it exits at a lower temperature. It would be
Excuse me,
about like
are you showing some images? We can see the first page only. Your topic details.
no. I that one I already showed that the section view. Now I'm describing that section view.
Okay,
So
thank you. Thank you.
okay, let me show you the section view again.
Stella, we need to speed up. We have limited time for each one of us, so make it fast. I think we have lost Stella. We have some technical problem. So, but we'll wait 1 minute for him. Otherwise, we will move on to Thursday. So I think it's better to move to Taslim, and we will come back after Salah joined after Taslim session. So Taslim, you can proceed. Yeah, I think Salah has joined now. Salah, can you hear me?
Yeah, I can hear. I'm sorry, due to some internal issues. I don't know what happened to the internet.
Yeah,
Suddenly
sure.
it
You
went
can
wrong. So,
continue,
okay.
Salah.
Can I continue? Okay.
Yeah, sure. I think we have lost him again. So Taslim, you can start your session. Yeah. Salah, you can wait now. Who is sharing this thing, Salah or Taslim?
Okay, what
This
happened?
is Salah's
This thing
screen.
are
This is
going to start?
Salah's.
Okay, okay.
Let
Yeah,
So,
then
Salah finish his topic.
Salah, yeah. Salah,
Salah, you can
please
continue.
continue.
okay, okay. So, as I said that this is the sectional view, so we can say like we can divide it like a primary side and secondary side. So the hot reactor coolant will about the 310 degrees Celsius. It will enter into the primary inlet, and it circulates the thousands of U tubes and exits at the lower temperature about the 280 degrees Celsius. And then secondary side, then that is like steam side where the steam produces. The feed water, it's about 230 degrees Celsius. It enters into the shell side of the heat exchanger. Then it absorbs the heat from the U tubes. In the U tubes, the reactor coolant is passing. So it absorbs the heat from the U tubes and it turns to the steam about the 275 degrees Celsius. Anything happen? Hi, am I audible?
Yeah, Salah, you are audible.
Yes, yes.
Yeah.
Okay. I think, okay, you can see my screen as well, right? Yes.
Yes.
Okay. So this
So,
is the just the general
Salah,
view of the
Salah,
section.
yes.
Yeah.
You have 2 minutes. You can conclude this session topic.
Okay. Let me tell you. So this is then I told during this one the working of a steam reactor how it is working. The reactor coolant will enter into the through primary inlet and will exit to the outlet, and meanwhile the feed water will be enter into the feed water in nozzles, and the steam produces. That is the working of a steam generator and how the steam is producing in a steam generator, and it passes to the turbine island, which then turbine drives and electricity produces. There. So, and what is the importance of a steam generator in a reactor operations? So, for the thermal efficiency, we need the for the optimal electricity generation. So, we need the efficient heat transfer then we can ensure the electricity, how much we can have to produce the electricity generate. So there is a very important role of the steam generator in a reactor. And also, as I said before, this is acting as a safety barrier and as like prevents the radioactive contamination from reaching the turbine island. And steam generator controls the reactor power output. So steam generator pressure influences primary system temperature and reactor power. Also, the steam generator acting as a heat sink during the shutdowns. And then the last topic, like what is the common issues is occurring in the steam generators. The main common issues are occurring in the steam generators are like tube folding and plugging, and stress corrosion, cracking, tube ruptures, and steam generator level control issues. The tube folding and plugging means that deposits or corrosion can block the tubes, and it can reduce the efficiency of the steam generator, and it will affect the total electricity production as well. And the stress corrosion cracking means the chemical attack on tube material, which can lead to the leaks in the steam generator. And tube ruptures means the leaking tube, which can mix the radioactive primary water with the secondary side. This is also very important, and it is very dangerous. And the last one, the steam generator maintenance and inspection. Usually, there is a main three type of maintenance and inspection, like a chemical cleaning. We know there is a steam generator blowdown process also occurring during the operation periods. It removes the sludge and it deposits to maintain the efficiency. And through plugging, the damaged tubes are plugged to prevent the leakage without removing the entire steam generator. And as usual, like for all, as like all components, the periodic replacement. Some plants replace the steam generators after several decades of service. So these are the main general maintenance of the steam generator in a power plant. So finally, we can conclude it like steam generator is a critical component in a pressurized water reactor nuclear power plants, and like the act as an interface between the primary and secondary circuits, like transferring heat from the reactor coolant system to generate the steam, and which drives the turbine generator for electricity production. Okay, thank you very much. I hope you got the someone all outlay of the steam generator, how it is working in the nuclear power plants, and hope you got. Thank you. So, is there any questions related about the steam generator? I welcome.
Yeah, thank you, Salah. Thank you. And guy, if you have any doubts or you need any clarification regarding this topic, we have 5 minutes. Salah will be there. He will be very happy to answer your question. Yeah.
Excuse me, Salah. Hello, am I audible? Hello?
Yes.
Sure, go on.
Oh, okay. As you said in between your presentation, there is a feed water circuit through the steam generator, right?
Yes.
So how much will be the temperature of that feed water, and how that temperature for the feed water, how it attains that much temperature? The feed water.
Usually the feed temperature of the of the feed water would be like 230 degrees Celsius, which will enter into the shell side of the steam generator. So from the feed water, feed water tank, it will come and it will reheat the water, and it will reach us up to 230 degrees Celsius, and it will enter into the steam generator with 230 degrees Celsius. then it will help to it absorbs the heat from, because the temperature of the reactor coolant that which is passing through the U tubes, that is about 310 degrees Celsius, and the difference between the feed water and reactor coolant about like 80 70 degrees Celsius. So then the lower temperature, the feed water will absorb the heat from the which is passing through the U-tubes, that is the reactor coolant. So then it will produce the steam. Then the steam passing through
Salah,
the
Salah.
yeah.
The question is the feed water, the secondary side, how
Yes,
it is
yes.
maintained that much temperature? How it? We know reactor core, it's producing heat. The primary side, we know how it is maintained that much heat in the coolant system. The question is how that temperature is obtained in the secondary side. If we are the
Yeah.
inlet, the steam generator, the feed water system is entering to the SG, right?
Yeah.
That feed water is maintained like 293. You said like that. So how that?
230 degree.
Yeah. Okay.
230, 250. Yeah.
How that temperature obtained achieved in the secondary side?
Yeah, there would be one reheater for the supply starting on the feed water system. So it will help to increase the temperature of the feed water.
Shabi, is it clear for you, or do you need any
Okay. Yeah,
additional
using
information regarding?
reheaters, feed water is heating to get that much temperature, right?
Yeah.
Yes.
So we can ask from where the reheater getting that much temperature? How the reheaters work? By a follow-up question.
Sorry?
If the like the plant is in the starting condition, how we can achieve that kind of temperature in the reheater? Right? How we are using that reheater to obtain that much temperature in the feed water?
That's a wonderful question. During the startup period, right?
Yeah.
Uh, let me check, then I will give, because I don't know the exactly. So
Yeah.
let me check
Yeah.
that, then I will give you the exact reply to, because
Yeah.
if I say anything something, because it will not be good. So let
Yeah.
me check
Sure. No
detailing, then
problem,
I will give
Salah.
you a response in
Is
the
there any other
coming sessions.
question?
Yeah.
Guys, is there any other questions to Salah? Put it now.
Not a question. Riaz, is there any electric heater or any type of heater?
Salah will be happy to answer that after he will check that one.
After main feed water pump, there is a very one high pressure heater is using for heating this coolant. After that, only it is directly going to the steam generator again.
Sorry, Tasmin, could you please elaborate and explain? I couldn't get you.
Can you hear?
Yeah, I can hear you, but can you please elaborate the answer?
No, once it is going to the steam is passing through the turbine, then it will then goes to the condenser, and this condensate pump, that means there will be a heat already. So it is direct. It is then passed through the main feeder water system with the help of these pumps, and then it is directly going to. There is a heater, HP heater, high pressure heater is there. So I think this high pressure heater is helping to obtain this temperature, and this directly going to then steam generator.
Okay, but my question is, while we starting the plant, how it is obtained? On the operation side, it's okay what you have said. There will be a preheater and a reheater. It's already generating heat, so it can maintain that heat. At
In the starting
question,
stage itself, the reactor producing some heat, a large amount of heat due to the fission.
yeah, it's in the coolant system. It's in the primary circuit. We are talking about the secondary circuit. If the feed water entering the SG,
Yes.
like Salah said, it's 230 to 250. How it's obtained at the starting stage?
I think this after this main feed water comes, it's directly going to a heater, a high pressure heater. So this will helps to reheat again, right? Is
Yeah.
there any specific answer?
Yeah, that's my point. How that reheater or preheater, how that's working? If at this starting of a plant.
Oh, at the starting stage, there is something to need to work the heater, right? Okay.
Okay, Salah will be checking on that topic, and he will be.
Yeah, definitely. I will give the reply on the comment section. Or
Yeah, sure, Salah. Thank you, and we will.
okay.
If no other question, we will move on to Thursday. It's already late. Is there any other question, guys? Yeah, sorry.
It's not a question, it's a doubt. See, in the primary circuit, there is a pressurizer. That's why the water is not turning to vapor, even though the temperature is as high as 300 degrees Celsius. But in the secondary, there is no pressurizer. Okay, then how come the water is not turning to vapor?
Yeah, Salah. Sure.
How
Before
come?
answering to that question, Salah, the primary section, the pressure is 155 bar or 15.5 megapascal. So what's the pressure range in the secondary circuit? What's the pressure in the secondary circuit? That's in the feed water system. You can answer that too.
Secondary circuit, actually that is not concerned because why? Let me check that.
You have already said about the temperature. Then it's a concern. You have to mention it, but you have to check the pressure also. That's what the follow-up question by Sai. What's the pressure in the secondary circuit?
From my knowledge, I think it's about 15 to 20 bar. Let me go. Just let me. Do you have any idea? Anybody knows? I
Okay,
remember
no
this
problem,
one value.
Salah.
Okay, anyway.
Salah, you can check and clarify
Okay,
and update.
Sai. Okay. Salah will
Yeah,
update us.
Shabir, if you have an idea, you can.
Because in seawater circulation, the temperature, as Salah said, is 70 bar. Okay. If the pressure is 70 bar, the boiling point of water is about 285 degrees Celsius. After that only the water will get boiled. Okay. So as Salah said, the temperature is only about 230 to 260. The temperature of feed water is 230 to 260. So the boiling point is 285 at 70 bar. So the feed water circuit maintains that much pressure, so it won't get boiled.
Fine, Shabir. Any idea how this high pressure is maintained without a pressurizer?
So they are using low pressure, high pressure heaters. So there should be some mechanism to keep the pressure in that boundary.
A closed loop, right? So there won't
Yes,
be any pressure leak. Okay, thank you, Shabir. Thank you, Sai and Sada. So let's move on to Taslim. Taslim.
Thank you, Reyes. Okay. Now we are going to discuss about turbine. Turbine. What is a turbine, and what is the function of a turbine? Means a turbine is located in the turbine island that is in the secondary loop. Okay, then what is a turbine? A turbine, the principle of a turbine is converting thermal energy into mechanical energy. And then with the help of generator, it converts mechanical energy to electrical energy, and the electricity is producing. That we already know that. And if we are connecting with and this slide is a little vast, so I just make some points to give a brief idea because we are having time constraints also. And regarding and what are the components of a turbine? There are the main components of the turbine is there will be a rotating turbine blades will be there. A turbine shaft, a single shaft will be there. It connects the high pressure turbine and three low pressure turbine and generator. It is connecting in a single shaft. In every nuclear power plant, there will be one high pressure turbine and three low pressure turbine. I will give you an idea about what is the use of this high pressure turbine and this three low pressure turbine. If we connecting this turbine section into the whole nuclear power plant function, we already learned and studied before that a large number of heat is producing. A large number of heat is producing due to the fission process. Once the heat is produced, this heat is circulating the reactor and it goes directly to the steam generator, and the water is flowing through the steam generator. It absorbs the coolant reactor. It absorbs the reactor coolant, and this reactor coolant is passing to the steam generator, and the steam is produced. Our colleague Mr. Sela already gave a detailed idea about the steam generator functions and importance and everything. Now this steam is produced and it is directly going to the high pressure turbine. This high pressure turbine is using helps to expand the steam, and the pressure will be reduced, and it is then directly going to the MSR. What is MSR? MSR means moisture separator reheater. If there is any excess moisture in the extra moisture content in the steam, it will help to remove, because without MSR, it will affect the high pressure turbine, like corrosion and rust everything. So once MSR removes the steam, it is then directly going to the low pressure turbine. There are three as we discussed before, there is 3 low pressure turbine. This low pressure turbine will helps to maintain the pressure, and it is the steam, and it works, the shaft works, and it helps to working the generator and produce electricity. And this steam is then directly going to condenser, and this condensated water is directly going to deaerator. Deaerator is using to remove if there is any impurities, like iron content. If there is anything, this deaerator helps to remove the impurities in the condensated water. And this one is helps to this one is why we doing means, otherwise it will affect this water is directly then going to the steam generator, so it will affect the steam generator. So after this deaerator, then it will then goes to the not deaerator, condensate polishers. Condensate polishers helps to remove the impurities, and this then will go to the deaerator, and this deaerator will helps to remove the if there is any unsoluble gases. It will remove the undissolved gases, and then it is directly going to the steam generator with the help of main feed water system. This is the total working principle of the nuclear power plant, and so it is the main turbine. A turbine also having a very important role, like steam generator and other such reactor vessel, such components. And if we if there is any malfunctions, and like we can consider a scenario that if there is any malfunction, like electrical due to an external event, the trip load, because if the supply loss, then what will happen? If there is anything such happens, there will be no resistance in the generator, and the turbine starts to accelerate rapidly, and the steam. It is only because of the flow is continuous, and it will leads to a turbine overspeed condition, which can damage. It's not normally, if there is turbine is overspeed, the turbine blade bearings and the connected system will damage. This bearing is mainly we are using to reduce the friction. So if there is any damage in the turbine blade bearings, it will affect very badly in the power plant. Then what is we already know that PWR in nuclear plant is over-engineered. Over-engineered means if there is any issues happen, they already considered some systems to remove these accidents. If there is any happen, there will be a system, not only for this one, in every area. If there is any accidents happen, there will be a system is already introduced to remove some issues. For that, one system is
Hello,
okay.
Tasneem?
So
Yes.
yeah.
Okay. Yeah.
Okay, fine. There is the first system is to remove if such accidents. Is one is turbine overspill protection system. That means TOPS. The primary what is the primary action of a turbine overspill protection system? If the turbine this turbine overspill protection system, it controls the system, detects first it will detect the overspeed because it is the normal speed is 1 ton percentage. If it is exceeding the normal speed, this TOPS will detect the speed, and then there will be a control valves. Then this acting so it will act very fastly. The control valves will act fastly and close the steam supply. So if the steam supply is cut off, then the turbine flow will stop. So the output will be the turbine will be back in control. The another system is turbine drip system. This also the same. If the speed is continuous increasing, the first one is if it is rapidly means exceeding the limit. The second one is it is continuously increasing. This drip system will activate. For that one we are using emergency stop valves. It is also shutting off the steam to the turbine. So the same effect, the outcome will be it will be in a, the turbine will be in the normal condition. This system also activates the steam bypass. There will be a bypass system and directly divert into the steam to the condenser. And the safety requirement, what is the safety requirement? If we can say that it prevents the turbine explosion damage due to the excessive. We already know that if there is any happened, it will be affect very badly to the nuclear, our nuclear system. So if there is in the turbine, there will be a bearings, lubrication system, and drain and vent system also will be there. This bearing system, I already informed that it helps to reduce the it helps to minimize the friction, and this lubrication system we already know that it helps to reduce the wear. And there will be drain and this drain and vent system, it is also using for there is any condensed steam, it is excess, it removes in the turbine casing. So these are all about the turbine, and we have already discussed if there is any malfunction and if there any happens, what will be the system using to cover this malfunctions. So these are all about the turbine, and if you have any questions, you feel free to ask. Hello? Hello?
Yes, Justin. Can you hear me?
Yes, yes.
Guys, if you have any question, please shoot. Justin is happy to answer your question. Guys, please switch on your camera. I can't see any.
No, yes,
We
all
can't
are
see you either. Yeah.
yes. We cannot see you.
Oh, sorry. Problem with my Wi-Fi, and I have connected in with my mobile data. That's why there is some problem. Network issues. Oh, sorry, guys. If you have any doubt This Taslim.
Taslim, do you know about turbine trip? What are the situations that can lead to turbine trip?
The same scenario that we discussed, if there is any trip due to any external events, it will happen. Turbine trip means electrical load supply will be cut off. So if it is cut off means the turbine will turbine will work very rapidly. There is no control in the speed, so it will affect the overall working. And for covering that covering that situation, we are using this TOPS, means the system like a turbine trip system or a turbine overspill protection system. Such systems we are using for to control such situations.
Okay, overspeed is a reason for trip.
Sorry.
So overspeed is one of the reasons for trip. Overspeed
Yes.
turbine.
Overspeed means it is because of the cutoff of this power supply. So the steam will continuous flow without any resistance, any control.
Can there be a situation where the turbine rotates beyond its designed speed?
Beyond its speed means the turbine rotates uncontrolled situation, right? Yeah,
that can cause turbine trip. No, if the turbine is rotating beyond, so there can be a limit, design limit. If the turbine rotates beyond that limit, then the trip can happen.
If it is the speed is low.
No, speed is more than the limit. If the turbine rotation is more than the set limit, like there is a design specification, design limit. If it is rotating more than that, then the trip can happen, right?
Yes. That times we are using this TOPS system because it senses the speed and it controls the valves and it's cut the steam supply.
Okay.
You said like turbine trip due to the reactor shutdown, right? Is there any other scenarios that may lead to turbine trip?
Turbine trip mainly it happens due to the power supply. Power supply cut off due to I think blackout is also a concern for the power supply cutoff. I think so. If there is any mistake, what I said, then one can clear.
I think Shabir have much more idea about turbine trip. It's more likely electrical related, I think. Shabir, can you elaborate on this
I
answer?
think that Taslim is explaining about the electrical generation side. If the grid connection is collapsed, if anything happened in the grid, the electrical generation should be stopped by any using the protection. The generator, the alternator will stop the generation. So once the generation of electricity is stopped, simultaneously the turbine should be stopped. Otherwise, the turbine will run more than the limited speed because it is at the no load. If the electrical load is zero, the turbine is also at the no load condition. So it will cause sudden speed rise because the load is suddenly removed.
Yes.
Load is removed means there is no steam to the turbine. There is no steam flow to the turbine. That's what you meant?
No. The steam.
There will be no. Yes, you can say.
I think first alternator is trip. or the generation of electricity is stopped. Then the turbine is running at no load. So the alternator is not generating any electricity. So the load is zero for the alternator and also for the turbine. So the turbine should be stopped, and also I think the reactor should be tripped at that time, or the power of generation inside the reactor should be reduced. So as part of the protection, the whole system will be activated simultaneously as part of the safety side. So we are explaining about the if once electrical generation is stopped, the turbine suddenly the speed of there is a chance of getting high speed suddenly. So we have to avoid that situation using TOPS, turbine overspeed protection.
Shabir, one thing, if the power loss happen, so there will be no connection with the generator. Then only it is rotating high speed, right?
When the generator alternator generation is stopped, the load on the turbine is also stopped, or it's also removed. The load is zero. So the electrical generation is also a load. So if the generation is stopped, then the load on the turbine is getting zero suddenly. So it's like a water hammer in the turbine. So if we close the valve suddenly, what will happen? The water will come as a water hammer. In same scenario, when the load is removed suddenly, the speed will get raised simultaneously. So there should be a protection for that, for preventing that scenario. So turbine should be protected.
Shabir, one doubt,
Yes.
Shabir. Shabir, you say that if the power generation is stopped, okay. So
Yes.
power generation stops means the turbine has to stop now. As long as turbine is
Yes.
running, power will be generated, right?
No, there is if the excitation is stopped, if the excitation to the alternator is not available, there won't be any generation of electricity in the alternator. So there is some protection systems for the alternator. If the generation is stopped, it's a scenario. There is no electrical generation. Suddenly the electrical generation stopped. The reason may accident or external events, anything like that. Okay. The scenario is electrical generation is suddenly stopped. That's all. Then the turbine, there is a chance of getting high speed. We will say the speed regulation. Getting the full load or the running load is suddenly removed. If we can take an example of a motor that is running with load, or we can take an example as a lorry is carrying a load, and that is running at a speed of 80 kilometer. Accelerator is at 80 kilometer per speed. Suddenly the load is lifted. At the same acceleration, the lorry will run very fast. You get the scenario. For the same example, if we remove the generation of electricity, at the normal operation, the turbine is running at the RPM, we can say at 1800 in 60 Hz, is rotating at 1800 RPM. If we remove the load suddenly, then the speed will change or will rise to a high value. There is a chance of raising that much speed. So there is a provision to prevent that scenario. That's all.
Yes, thank you. Thank you, Shabir.
Thank you.
So I think it helped get you a basic idea about turbine protection systems and all. And if there is any more questions, Taslim will be happy to answer you. Is there any other questions? Nimshad, Salah, Suman, Vinayak. Okay, then we'll move on to Sainath. Sainath, you can start now. So guys, we are now moving to instrumentation team. So Sai will start this session and following him start and myself. Continuing INC. Okay, then Sai.
Okay.
Yes, sir.
Okay. I'm going to walk you through the nuclear instrumentation system with a specific focus on X-core instrumentation system. We all know that nuclear power plants rely on precise and reliable instrumentation to monitor and control reactor operations safely. Among these, the X-core instrumentation system plays a crucial role in measuring neutron flux from outside the core, ensuring safe and efficient power generation. In this session, we will explore the working principles, components, and significance of X-core detectors, their role in the reactor protection and control, and how they contribute to overall plant safety. Okay, so let me share my slides. Okay. Please confirm once it is visible.
Yes.
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 Okay, so we are starting with the X-core instrumentation. These instrumentation systems are the instrumentation systems, measuring instruments which are located outside the reactor core. These instrumentation systems will detect the leak neutrons, the neutrons which are leaking in the reactor core. These neutron flux is detected by these instrumentation systems being produced inside the reactor vessel. You can go through the definition here. I'm going to the next slide. So there are four major purposes for X-core instrumentation. The first one is to provide indication of the reactor power from shutdown to full power conditions. The second one is to provide input to the reactor protection system during startup and power operation. The third one is to provide reactor power information to the automatic control. And finally is about axial information during power operations. Going to the third slide. Visible.
Yes. Yes.
So you can see those yellow highlight. These are the locations where the X-core instrumentation systems are located. Going to the next one, next slide. So as I earlier mentioned, it monitors the power level of the reactor by detecting neutron leakage from the core. There are two reasons why these instrumentation systems rely on the leakage of the neutron, leak neutrons. The first one, the leak neutrons, this flux will be directly proportional to the power inside the core. Higher the power, more will be the leakage rate of the neutrons. And it is easier to design and maintain neutron detectors that do not operate within the hostile environment of the reactor core. So these detectors are positioned outside the reactor vessel. So if the detectors are inside the reactor vessel, they are constantly irradiated. That can cause damage. So it is easier to maintain the detectors which are placed outside the reactor vessel. Going to the next slide. So the X-core nuclear instrumentation system is capable of detecting both axial and radial power distribution. Both are necessary. So I'm going to next slide, where you can see the representation of a detector. A detector is just a cylinder, gas-filled cylinder. You can see a cylinder here. It's filled with gas. So this is how it works. I will tell you in the next slide. So there are two types of radiations going inside the detectors: neutrons and gamma radiation. So they will directly ionize the gas inside the detector. So this will produce electrons and positively charged ions. So in this picture, you can see that the positively charged ions, they will move towards the cylinder, to the shell, and the negatively charged electrons, they will move towards the center of the cylinder. Because the center is negatively charged and the cylinder shell is positive, sorry. The positively charged ions will move towards the cylinder shell, and the negatively charged electrons, they will move towards the center of the shell, center of the cylinder, which is positively charged. So this movement will create this electric current inside the detector. This current is measured to measure the power inside the reactor. And neutrons are chargeless, and so in order to detect these neutrons, we need something, a target nucleus inside the detectors. We are using boron as a target nucleus. So the neutron will interact with this boron and will produce lithium, helium, and electrons. Lithium and helium, they are positively charged, and electrons are negatively charged. So these positively charged ions, lithium and helium, they will move towards the cylinder shell, and the electrons will move towards the center of the detector, creating a current that will be measured later to measure the power inside the reactor. The X-core instrumentation system consists of three subsystems: source range nuclear instrumentation, then the intermediate range nuclear instrumentation, and the third one is a power range instrumentation. We will start with the source range detector. The source range measures the lowest level of power. It uses boron trifluoride detectors. So the boron in the gas, it will help to detect the neutrons in the radiation. And in the source range, the gamma radiation is not directly proportional to the power inside the reactor. So there is a limitation. The gamma radiation directly ionizes the gas in the detector, creating a potential problem. At low power, the gamma radiation is not proportional to the reactor power. We have to remove its effects to have the detector present the reactor power. We have to remove the gamma radiations. It's from the measurement. It's not to the reactor power. So we will consider only the neutron effects. So there is a process we use to exclude the impact caused by the gamma radiations in source range detectors. As you can see, the electronic circuit that is used to detect this radiation sees individual pulses caused by the neutron and gamma interactions with the detector. We do not want to include the gamma pulses in our measurement, so they need to be ignored. Fortunately, the neutron pulses are much larger than the gamma pulses. This allows a process called pulse height discrimination to be used to eliminate the gamma pulse, so that only the neutron pulses are counted by electron. You can see here that the pulses caused by the gamma radiations are of lower height, and the pulses caused by the neutrons are taller, higher. So we just exclude the lower pulses, which are the pulses caused by the gamma radiation, remaining only the pulses caused. This is the process which I said in the previous slide, the pulse height discrimination. Here in this picture, you can see source range, intermediate range, and the power range, the range of these three detectors. If you check the source range detectors, you can see that the source range detectors overlaps the lower decades of the intermediate range detectors, and the intermediate range detectors overlaps completely the higher decades of the source range and completely overlaps the power range detectors. You can see that, and the power range detectors overlap the higher decades of the intermediate range detectors. So this is explanation about the intermediate range detectors. The intermediate range detectors uses a detector called compensated ion chamber. The reason why this is called a compensated ion chamber, because we are excluding the pulses caused by the gamma neutrons. These are just two concentric cylinders. The outer cylinder is lined with boron, and thus the inner cylinder will have only boron. So it detects only the gamma. Sorry, the inner doesn't have any boron. It sees only the gamma. The cylinder with neutrons will detect both gamma and neutrons. It's a pictorial representation of the detector, intermediate range detector. So you can see that there is one cylinder, the upper one, the chamber with boron coating. So it will detect, you can see two lines, gamma and neutrons going inside it, and both gamma and neutrons they are detected by the that cylinder. And the below one, here you can see the neutrons are not detected, only the gammas are detected, because it has no boron inside it. Okay, so the signal gamma from the upper cylinder, the gamma, and it detects both gamma and neutron. The lower cylinder will detect only gamma. So we will subtract these gammas, leaving only the neutrons. So that's how we are excluding the gamma, leaving only the neutrons. The last one is the power range detector. Power range detectors is the highest range detectors. Except for startups and shutdowns, the reactor operates in the power range. The power range uses an uncompensated ion chamber. Because the compensation is not required here, because the neutron flux will be directly proportional to the power inside the reactor. That's the reason. That's what here we are saying here. At the higher power levels, where the power range operates, gamma contribution is proportional to the reactor power. So no gamma compensation is required here. So this is the last slide, and I'm concluding here. Any doubts?
And this best you can ask related to for instrumentation if you have any doubt related to this topic. Please, we have 5 minutes. We have very time constraint, so we have to move fast. Nice. Suman, Vinayak, and Shabi, Bella, Nisha.
Sai, how about the maintenance of these detectors and what are the process?
Sorry.
How about the
Can you please
maintenance of,
repeat?
yeah, for these detectors? How about the maintenance during the for all periods? So what is the periodic, like any
No,
1 year
actually,
during?
no,
Yeah.
I don't know how often these instruments are the periodic maintenance. I don't know about that.
Is there any periodically checking? Is it working properly? So is there any method to?
There will be calibration and maintenance, but how often it is done, I have no idea. Maybe after
Sai, please
every cycles. Hello.
please check that and update in the group.
Oh, sure. I will check that and let you know. Note
Okay.
it down. Okay.
Stella, if you didn't get the answer, please raise your question again in our group. So Sai will address that.
Okay, sure.
Yeah. So now let's move to other. There is no other question. So please respond. If you don't have any question, we can move on.
Yes.
Okay. So everyone is clear about S4 instrumentation, I think. So let's move to Nimshat. Yeah.
Hi, good evening all.
Good evening.
Can you see my screen?
Yes.
Nimshat.
You can see.
Okay. So today I will give a brief idea about what is instrumentation control in systems in nuclear power plant. So we'll go through just the introduction of instrumentation control system, then two systems like process control system and nuclear instrumentation system throughout the session. Okay. So so what is a instrumentation control system? Actually, instrumentation control systems are vital for safe and efficient operation of nuclear power plants. Okay, these systems gives us a real-time monitoring and control of critical plant functions. And the key systems in nuclear power plants are, there are main 5 systems in a nuclear power plant. Nuclear means instrumentation control system. There are process control system, nuclear instrumentation system, road control system, road position indication system, and reactor protection system. So today we'll go through these first 2 systems, process control system and nuclear instrumentation system. The instrumentation and control systems in the nuclear power plant serve 4 primary functions. First one is indicating important plant parameters. Second one is providing alarms when parameters fall outside normal operating ranges. And third one is feeding input to control systems like steam generator level and road control. And fourth one is feeding data into reactor protection system to ensure plant safety. My voice is audible, right?
Yes.
Yes, clear.
So now we'll go through process control system. Okay, what is a process control system? The main function of the process control system is for measurement, indication, and control of level, temperature, pressure, and flow in plant systems. That this is the primary function of a process control system. These systems provide actually critical data inputs to the reactor protection system also. So we'll get a measurement, indication, control of level, temperature, pressure, these all parameters, and will give a input to the reactor protection system. Here, the protection of the safety is a main thing, like which are responsible for the protecting the reactor fuel, pressure boundaries, and containment structures from potential damages. These process control systems plays a dual roles actually, for like managing plant operations while also ensuring the safety and integrity of the reactor itself. And second one is like by continuously monitoring variables like pressure, temperature, and they give a real-time data to operators, enabling them to take a corrective actions if needed in case of any pressure drop or temperature increase or decrease. So these systems will give a real-time data. So according to that, the operator can adjust the value, corrective actions they can take. So I'll give a few examples of control systems. Like there are mainly 5 control systems in nuclear power plant. They are like a steam generator water level control system, to then pressurizer pressure control system, pressurizer level control system, temperature control system, steam dump system. So we'll just go through one example, like we'll go through one pressurizer pressure control system. So you can see the diagram. Here, there is a pressurizer pressure detector. Okay, this pressurizer pressure detector measures the actual pressure in the pressurizer. After that, this signal goes to controller, which will compare the measured pressure with the set point. Then this output of the controller regulates the pressurizer pressure. How it will regulate? By turning on heater or opening spray valves as is necessary to maintain the required pressure set point. And in this diagram you can see some protection systems, 4 blue boxes actually. These represents actually
sorry,
safe. Yeah.
sorry, Nimsha, there is something that is blocking the slide.
You cannot see my slide?
Not Nimshad, you are minimizing the cube. I mean, our team
No.
app.
Now.
So that team app is displaying in front of your head slide.
Now it is visible?
Not yet.
Yeah?
No.
No? The thing is, I'm sharing from my phone. My laptop
Yeah.
charges finished. I'm in car actually. So Riaz, can I share you the PDF? Can you
Yeah. Yeah. Sure.
Shabir?
You're sharing it in WhatsApp, right?
Yeah, WhatsApp. I shared in your person.
Yeah. Yeah. I got it. I think it's better to share with someone else because my net is too slow, not download.
So I'm
You can
forwarding to
share
the
it to
group.
me. Yeah,
Yeah. Please share
I'll
to
share.
me.
I forwarded in group. Can you see this opportunity?
Kalpana, right?
Hello. So you can go down.
Seven. Okay. It's seven.
No, yeah. So so you can see the diagram here. Okay. So in this, there is one pressure detector. This will detect the actual pressure in the pressurizer. This signal it will goes to the controller. There, the controller, what it will do now, it will compare the measured pressure with the set point pressure. Then the output of the controller regulates the pressurizer pressure by turning on heater or opening spray valves as necessary to maintain pressure at set point. And you can see some four blue boxes here also, protection systems. These represent safety related functions actually. There is a high pressure reactor trip, a low pressure reactor trip, and a low pressure safety injection system. And there is a valve closer designed to isolate a stack open pressurizer relief valve. So these are all protection systems. So these pressure detectors give signals to these systems also for a protection side. Okay. Any doubts? So when Next slide. So now we'll go to
Hello. Yeah, yeah, theoretically.
look about. Hello.
Yes, proceed.
Okay. Nuclear instrumentation system actually plays a crucial for measuring the reactor power in pressurized water reactor. Okay. There are two types of nuclear instrumentation systems we use in a nuclear power plant. One is ex-core and in-core systems. As my colleague, our colleagues said, explained about the ex-core systems. These two systems provides a comprehensive view of the reactor power output, actually. While the ex-core system provides a continuous measurement of total power, the in-core system offers detailed insight into the core power distribution inside the core power, how the power is distributed, and helping ensures that the reactor operates safely and efficiently. Okay, next slide. Vinayak, next slide. So we'll just go through X-core and in-core nuclear instrumentations. The X-core nuclear instrumentation systems uses neutron detectors placed outside the reactor vessel to measure neutrons that leaks out of the core. The neutron leaks is proportional to the total power output of the reactor. These systems includes actually three subsystems. The first one is source range nuclear instrumentation. Second one is intermediate range nuclear instrumentation. Third one is power range nuclear instrumentation. Each of the systems is designed to handle a specific range of power levels from reactor startup to full operation. Together, they can ensure that the reactor is continuously monitored for any variations in power output. Next one is in-core nuclear instrumentation systems. This system is designed to measure neutron flux directly within the reactor core itself. These systems uses actually miniature fission chambers that are inserted into selected fuel assemblies within the core. These detectors can produce a detailed map of the power distribution inside the core, allowing the reactor engineers to monitor the performance of the core more accurately and look for any unusual local power peaks. And these detectors are not in constant uses, actually. They are periodically inserted into the core to gather data and are withdrawn once their measurements are completed. While they provide valuable insight into the reactor's performance, they do not directly feed into the reactor production system. One of the system is aerobol system. Next one. So in both process control system and nuclear instrumentation system are critical to the safe and reliable operation of NPP. These systems not only control and monitor essential plant parameters, but also provide the necessary data to ensure reactor safety and prevent damage. As technology continues to advance, these systems evolve to meet the increasing demand for safety, precision, and efficiency. So that's it. Thank you. Any doubts?
Thank you, Nick. Guys, you can ask any doubts related to process control systems in instrumentation, and as well as nuclear instrumentation. I think Sai had already covered the X-core instrumentation part. So a very brief info nuclear instrumentation had been done by explanation has been done by Nimshad, and he had done a very good process control system explanation with an example. I think pressurizer pressure control system. You guys have got any doubt in these topics? You can ask now.
Hey, Nisha, your mic is mute. Nisha.
Yeah, you can ask the question, Shibu.
Okay, as you said, there are two types of instrumentation. One is for the during normal operation for the process control. Instrumentation is for normal operation, and also as part of the protection also instrumentation measuring is giving the signals, right? So is it one system, or is there any separate system? One is for protection and another for
It actually means process control system. It will give a real time data. We can measure and it will show indication. And in same time also it will give a protection side. It is having a protection side.
so
you
the
have seen
same
that
system will give the signals to the
protection system.
process and also for the
Protection system. Yeah.
It's like Shabir, I'll try to give a different perspective. Like it is measuring the process variables like pressure, neutron flux level, whatever it is, and it will be going to the controller where it will check with the set point. So there will be two systems. Like for the normal operation, there will be a process control system, and there will be a reactor protection system as well. So from the control element, process elements, it will go to the controller, and from there, it will check with the for normal operation. It obviously process control system will have the set point, and it will be working on that. And if there is any abnormal condition or any set point value exceed, and if there is a chance for an accident scenario, then the same process element or controller will detect it, and it will bypass all the normal operation, and it will directly go to the protection system. It will change over to the protection system.
Okay. Thank you.
Is it clear?
Yeah, it's clear.
Is there any other doubt? Related to process.
Yeah.
Yeah.
Just we discussed about the process control system and instrumentation control system. So this all system we are using to find the parameters like variation like temperature, pressure, like that. So
No.
if there is what I'm asking is if there is any variation, if we detect, is there any we have any safe period system we have to take sudden action?
Yeah. Okay. Actually, these systems are in INC. There are many systems. Okay, I have mentioned 5 systems. So out of that process control system, what it will show now, it will measure the parameters like temperature, pressure, flow, everything. So it will give a real-time monitoring for the operator also. It will give, if in case, I will give example, if the pressure drops very low, so it will give a signal to the low pressure detector in a protection system. So it will go for the reactor trip. That maybe in a chance I'm saying, okay, for example. So process control system means process variables like temperature, pressure, these all kind of stuffs will be measured, and it's a control system. Okay. In instrumentation system, it uses for in measuring the neutron fluxes, the power of the reactor. So X-core and in-core, what it will measure is neutron flux inside the reactor and outside the reactor. So by calculating that, we will get the reactor power. So there are another system like a road position system. So we'll come to know where is the control rod position. So you got my point, right?
Michelle. The question is how? If there is an accident scenario, is, the operator should operate, or the system will automatically do the work?
The system.
That's what question was.
The system, I think it will be automated. Maybe for specific, if it is going very low in case of pressure, if it is going very low, up to a certain below a certain point, maybe it will go automatically for a trip. So I didn't go through that much deeper. So I will get back to you guys after.
Firstly, actually, the protection system is very crucial and critical one. So if there is any signal going to accident scenario, or say if any set point in the controller exceeds, it surely overrides the operator, or we don't need any operator should do anything. The protection system will automatically take over from there. Is it clear?
Here the safety is our main priority. So
sudden action will happen if there is any variation, of course.
Yes.
Yeah.
In first stages, there will be some bypasses. We can rectify. They will try to rectify that problem. If it is not, it is beyond that, then it will go for a trip, I think.
So, thank you.
AOO condition, there will be some transitions. It will be. We don't need a reactor trips for AOO. So like
No.
That it will be like going to a reactor protection system trip or something. Okay, guys. Is there any other questions?
Riyaz, any idea about the working principle?
Not me. Nimshad.
Nimshad.
Yes. Go on.
Any idea about the working principle of in-core instruments? I tried to understand, but I could not understand. I read about it.
No, actually, I didn't go through that deeply.
Okay, fine.
Let me check and I will get back to you.
I think, Sai, we already shared in our PDF.
In-core, not airball, normal.
Airball
No, not about airball. Self-powered neutron detectors.
PNDs, yes.
Yes.
Yeah, we already shared one PDF in the.
I've gone through that, but I did not understand.
Yeah.
Actually, I wanted to include in-core instrumentation. I did not understand. That's the reason why I excluded.
Yeah, okay. In the coming sessions, we can go through that in detail. Okay. Yeah. So, guys, thank you, Nimshad. It was a wonderful presentation, and we will move on to next topic. And
Riyaz, I'm leaving actually. Yeah. I'm outside, so it's 9:30 here. So you guys continue.
Yeah. Okay. Nimshad.
Okay. Thank you.
Okay, guys. I think it already took more than 1.5 hours now. It's so further. No. So let's. Today's my presentation is control channels and two mode
Yes, are you
operation of.
sharing something?
Yeah.
Yeah,
You can. Yeah. Okay. So today's my topic is control channel, and I will briefly explain about the two mode operation of a nuclear reactor. So before going deep into the control channels, I think you guys have a idea about what's a process variable and what's a process. I'll just give a brief idea about this, and we will jump to control channels after that. Like process variables, we know for the temperature, pressure, level, flow. These are the variables that should be measured. Like in order to maintain a safe and efficient operation of an NPP, we need to get the real-time value of these parameters. So we to get the real-time parameters, we are using some process elements like thermocouples to get the temperatures, like all other variables. We are using some elements to get the respective variables. So I think you guys got an idea about what's a process variable and what is a process element. And once we get the value of the process variable to the process element, that particular value will be moved to a controller. Or from there will be one set point, and it will be like a closed loop, and it will be giving a desired output. And what Nishad was explaining lately about the process system. So I am not deep diving into that process system. I think you got an idea about that. So in a bigger picture, we will say like systems. We will be having, we have to monitor and measure and control. These are the basic thing to operate and operations and safety of a nuclear plant. This should be always maintained. So this system, like the main control parameters of a nuclear power plant, like we can say like the RPF temperature, the steam pressure, the pressurizer level, and the pressurizer pressure, and the steam generator level. This can be like a control channel. Okay.
Yes.
So if we can say the definition of a sorry.
You are not audible.
Yeah,
Can you hear me?
voice is breaking.
Okay, is it clear now?
There is a lag.
Yes. I that my
Yes, can you share this PPT in group? I will share the screen and you can just use your voice.
yeah. Yeah, you can't see my
We can see your screen, but your voice is breaking. Maybe while sharing the screen, it may affect the internet. So at least we can hear the voice perfectly.
And with my hello.
Hello, did you share?
Yeah, I have
Yes, you are sharing the WhatsApp, right?
sorry.
Are you sharing the file or are you sharing the screen?
Are you got the file? Yeah.
Hello?
Did you get my file?
No, not yet. You message it me personally or in the group, both I didn't see.
I have message. And again. Um, Am I audible now?
You're audible.
Yes.
So can I continue?
Yes, yes. You can start from
I-
the what control channels.
Yeah. So the control channels will be always monitoring the parameters, the plant parameters to achieve stable and safe operation of the plant. It's like a bigger picture from the process variables and process elements. It will be monitoring all the system. So that's what control channels are. So they have in this slide I have given you some main control parameters of an NPP. So next we will move on to the two-mode operation of an NPP, two-mode operation of an NPP. So In that two-mode operation, we are having, if the plant is a starting stage, it will be like the plant power level is like less than 25% of full power, then the mode is in neutron flux mode, neutron flux control mode, we can say it like that. And if it is above 25% of the full power, then it is in the ACT control mode. ACT means average coolant temperature. So these are the two control modes of operation of an NPP. So in this figure, we can see like it's
Riaz, can you repeat once again? Can you please two control modes?
Yeah, two modes of operation. In an NPP, there is two modes of operation in terms of power. If we are taking the parameters of power, we can say if it is less than 25% of full power, then the mode will be neutron flux mode. And if it is above 25%, it is in ACT control mode. ACT means average coolant temperature. Okay. So then you can start like that. You can say the primary average temperature set point. In this figure, it's like in the x-axis, it's saying power level percentage.
Figure is
now
yeah. Visible.
Yeah. And in y-axis, it is the temperature, degree Celsius. So in this figure, it is only showing about the ACT control mode. We are deep diving into the ACT mode, ACT control mode. After that, we will discuss about the neutron flux control mode after this. So the red line is showing an hot leg, and the black one is showing the average temperature, and the blue is the cold leg. And the green one is the steam generator saturation temperature. So at the cold leg, at the starting point, like if it is above 25% of full power, it's obviously in the ACT control. It's what it's showing here. And the starting temperature is inside the reactor core will be, the core leg will be 303. And the pressure will be 90 bar. In order to get that, it's in the secondary side, it should be in 90 bar. And the temperature is 303. So the steam generator saturation point, the cold leg will be dropping. If it is rising, the power level is rising from 25 to 35%, the cold leg temperature will be dropping, and the average temperature is maintaining a constant level. Actually, the ACT, what is in ACT means we have to get what the power demands. If the turbine is rotating at the power needs, the reactor power, it will be equal to the power generating inside the reactor, like the heat, the thermal heat, it will be proportional. Whatever the generator is producing, it will be directly proportional to the reactor power inside the reactor RPV. You got my point, I think. Is it clear?
Yes.
Yes, Riaz.
Yeah.
Yeah, sorry,
So,
for me it is not clear. Sorry.
Yeah. In ACT control mode, that is, it is greater than 25% of full power. In whichever condition the turbine, the generating side power will be equal to or directly proportional to the reactor side power. If the generator side is reducing,
Power generation. Sorry, the power generation is directly proportional to in
The reactor,
ACT.
reactor
What?
Yeah, it's like it's a primary and secondary control channel. It's controlling the using the temperature. It's controlling the working of a reactor as well as the turbine. With these two parameters, it is controlling the output. Like whatever output we need from the generator, it will be directly proportional to the reactor power, thermal power it is produced. Like if the plant operates greater than 25% of its full power, it is in ACT mode. So what ACT mode means? Whatever generator is producing, it is directly proportional to the reactor. It can be equal. So it means if it is 25 to 35, it will be maintaining that pace. If it is increasing, automatically it will be increasing in the RP. If it is the generator side, it is increasing, again it will be increasing the, if you can look into the figure, like if it is increasing from 35 to 60, then the reactor side, we don't need to do anything extra or any. The primary and secondary control channels in the ACT control mode, it will be detecting it and it will be automatically adjusting our the control rod position in the CRDM and all are interconnected. It will be maintaining that required output. You got my point? So you have to understand only like this. If it is, you can work if it is, we have only two modes of operation regarding the power level. Using the power level, we are having two modes of operation. One is ACT control mode. It is average coolant temperature and neutron flux control mode. If it is above 25%, it is ACT. So it is if it is ACT, then the turbine is directly proportional or equal to the RPV power. You got that? So
Okay.
if it is below 95, 25, it is neutron power control mode. You can see in this here, this time, this power frame, it will be neutron control mode. And if it is in this one, it will be ACT control mode. So what's the difference means in neutron control mode, that is below 25% of full power, the neutron flux or neutron power will be greater than the generator side. Why we are keeping like that means how we are keeping means we are keeping like we have all the MSB like bypass system. So we will be keeping MSB open. The excess steam will be bypassed and it will be condensed and it will be given back.
Why we are bypassing?
Oh, we already told you the neutron power is greater than the generator side power. So it will be excess, right? In the primer side, it is excess. If the neutron power or the RP or the reactor side power is excess than the output power, then we have to do with the steam, the extra steam that we are producing. You got my point. Below 25%, if the plant full power is below 25%, then the in primary side power is greater than the secondary side power. So the primary side steam generation is higher.
Riyaz. What is secondary side power and primary side power?
The primary side means the power what we need. Yeah. What is in primary side?
The primary side, the primary circuit. But what is primary power and secondary power?
Where we are getting the power?
From the reactor.
Yeah. That's what primary power.
So what is secondary power?
What we are generating. Got the picture? Sai, if you have doubt or not clarify fully, you can ask. I'll try my best to clarify you. So you can ask questions. Sai, is it clear?
Riaz, is there is any
Yes, sir.
representation as you mentioned here for primary and secondary power?
We don't. What kind of representation you mean there?
So here, what is the difference of 3 bars is shown here?
This is
What is the green dot and the black dot is representing?
This one is like MSB, the black dot, and this is the steam generator pressure drop. This is entirely different. I am not explaining this one. You can see this one. I am with power level and temperature. I am explaining now with power level and temperature.
Okay.
In that, the x-axis is same. That's why I am mentioning here. That is, this x-axis is both are power level. So I'm talking about before I had give you a brief idea about ACT. I think, is it clear about ACT?
Riaz, the power generation will see during this NCT. What is that NCT?
ACT.
No, not the below 25%.
Neutron flux mode.
Neutron flux mode. So below 25% of reactor power, the power generation will be less, right? Power generation means electricity generation will be less, right? Very less, right? Correct.
Yes.
Then why you said that during this NCT that there will be more flux? This side it will be lower, that side will be higher. Because in secondary side, power generation is directly proportional to the how much power is being generated in the primary.
That's what I am saying, Sai. It's in ACT mode. It's in ACT mode. It's directly proportional. This is another scenario. Less than 25%. We are talking about two mode operation. One mode operation we already covered. Like if it is greater than 25%, it is directly proportional or equal. Like primary and secondary we already equal. We are going to this. We are just saying about the second scenario. Like if it is less than 25%, it is another mode, like neutron flux mode. In neutron flux mode, the primary side will be higher. Why? How it is making that high position? That's what I said. Like it is using by the main steam bypass. Like excess heat steam will be bypassed and condensed. You got that picture?
Why it has to be bypassed? That's the.
If primary is greater than secondary, there will be excess steam, right?
See, and now tell me, the scenario you are telling is currently we are in ACT mode and we are going down to neutron. What is that other
neutron
mode?
Flux mode. Neutron flux.
This is the scenario. From ACT we are going down to. That's the scenario you are explaining.
ACT is another mode and neutron flux is different mode.
That is okay. So just imagine the currently is in ACT mode. We are going down to this 25 below 25. From ACT we are going down.
Yes.
this is a time where we are bypassing the steam.
Yeah, if it is below the 25% of full power, that means the output power, the secondary side power is very less, as you mentioned earlier. It will be very less. But the primary side, the reactor side power will be excess. So there will be excess heat. So that heat should be bypassed.
Okay.
See, Sai, if there is, how we can explain that? Any others have any idea about any other perspective about this one? Is anyone got the point? Kabir, Vinayak, Salah, Sumit?
I think, so if we normally during the operation, the reactor is generating the heat. Accordingly, the alternator is generating the electricity simultaneously. The
What
plant
is
operating.
alternator? What is alternator first?
Electrical generator is known as alternator.
Okay.
In electrical term, electrical AC generator, we call it as alternator.
Okay.
It's a generator generating AC electrical energy, normal generator. Technical name is alternator. Okay. This, if the load demand is reduced, so the required electrical generation is reduced. But the generated heat in the steam generator produced the steam. But the required electrical energy is reduced. At that time, we have to bypass the excess steam.
Okay, so
It's
we are
continuously,
we are suddenly decreasing the power.
no,
That's the
it's continuously, I think it's continuously running as per the requirement. Power may vary. So
okay.
whenever the required electrical generation is reduced, then we have to bypass little bit amount of steam according to the reduction
okay,
in the electrical generation.
got it.
It's a part of protection. So the system will operate within that limit.
Okay, I got it. Riaz, I got
Once
it.
it bypassed, okay.
Is this same you are saying, Riaz?
Yeah.
Okay, fine then.
Okay. I think these are the two modes, and I will conclude that one with. Okay. This is a very big topic, and we need more time. Like it's have like saturation points and the bars and the pressure bar that Vinayagan were asking, and how it is controlling the CRDM. It is all interconnected. From this, they are controlling the road position system, and it is going to the RPS and road speed program, stretch out principles are there. So I think for another day we will be explaining that. To conclude, in short, we were discussing about what's a process variables and process elements, and we got a brief idea about the control channels and two-mode operation of a reactor control system, like ACT control and neutron flux control. Thank you, guys.
Riaz,
Yeah.
before we close, Riaz, just one more.
Yeah, sure.
question. Okay. See, Riaz, for example, let's take this steam generator water level control system. Okay, for that there will be only one control channel dedicated for steam generator water level control.
I don't know.
Okay.
I think control channel is a very big topic, and if we go in deep, like reactor control system, there will be some control channel. It will be constrained about consist of some 2 or 3 systems combined, like primary and secondary side. So if anything happen in any way, it it will be in normal operation as well as in safety protection system. It will be it's like we can say independent and reliable and redundant systems. All are combined. Like we will be having 4 trains, and out of 2, then it will be act accordingly. So it's a very big topic, and we need to cover like sketch out principles and how the system going to monitoring and system, how the protection systems are acting, and how the temperature, not temperature, how the neutron flux that the power constraints are controlled by the variations that happening inside the control channel, or according to the variables that we have measured. So I think for another day we will be discussing that in detail. So is there any other questions regarding the 2-mode operation? Is it clear like what's an ACT and what is a neutron flux, right? Have to think about only the full power. If it is below 25% of full power, it's in neutron flux mode, and if it is greater than 25%, it will be average coolant temperature control mode. So I think, and in that one, you have to get like if it is ACT mode, the like reactor power is matched with the turbine power in steady state conditions. That's the point you have to note. And in neutron flux mode, neutron flux set point must be greater than turbine power to ensure reactor stability. Okay, guys, that concludes my presentation. So if you don't have any further questions, we will move on to Vinayak.
Vinayak, can I take before you presenting? Because after 12 p.m. we have some issues with the material.
Sorry, come again.
Riaz, can I present before Vinayak? Because
Yeah,
sure.
please.
So, guys,
we need to wind it as up. It's already midnight.
Yeah.
So, Shabir, you can make it for the rest of the people.
Yeah.
You can stop the sharing, Riaz.
Yeah, sorry.
So hi guys, I hope my screen has visible in your app.
Yes, please.
Right. Okay. So I would like to share some insights about the reactor coolant pump. So we have already well known about this topic, reactor coolant pump. In technical term, we call it as RCP. So here, the picture clearly visible. The center of this picture is the reactor, and there are 4 steam generators and also 4 reactor coolant pump and 1 pressurizer. Clearly, it's a 4-loop pressurized water reactor. In this, we are going to concentrate on one component that is critical. The name is RCP. So here you can clearly see the RCP, the sectional view of a RCP. In this, we can see it's a vertically single stage centrifugal pump. That is simply RCP. You can see the construction. The top is the motor. In between, there is a shaft connecting between the motor to the impeller. In this impeller circulates the coolant. As we know, there are 4 RCPs. Each and every RCP is independent, but togetherly they are providing the force circulation. The RCP is located on the cold leg of the reactor. As we all know that the reactor is generating the heat in the fuel. So we have to take that heat from the fuel to the steam generator for generating the steam. So for that purpose, we are creating forced circulation of the coolant through the reactor. For that RCP we are using. So togetherly, 4 RCPs generating the forced circulation of this coolant. It takes the coolant through the reactor up to the steam generator. So the coolant is having the temperature above 300 degrees Celsius and pressure boundary is about 170, above 150 bar. So when the coolant flowing through the pump, there should be that much temperature that has to be carry this motor, this RCP. So there are 2 types of coolers provided, depends upon the design. There are air coolers and also oil coolers for the cooling purpose of this RCP. In this, I am concentrating on the electrical side of this RCP. Simply, the RCP is an 3-phase squirrel cage induction motor. There are 2 types of 3-phase induction motors. One is slip ring induction motors. Other one is squirrel cage induction motor. Here we are using the squirrel cage induction motor. In capacity, it's about 10,000 HP. 1 HP is equivalent to the 746 electrical watts. So when we are calculating the required energy for a RCP is about 7 megawatt. We are calculating the energy consumption. The electrical supply voltage required for RCP is ranging from 6.9 kilovolt to 13.8 kilovolt. It may vary, it depends upon the design. As I said, the pressure is the primary pressure boundary is up to 176 and the temperature capacity is up to 350 degrees. That much design have to be done on the RCP. For RCP, it's a crucial and important component. So it's included in the class 1 electrical system. That's directly related to the safety system. So the supply for each RCP should be physically separated and should be electrically isolated. The protection system also physically separated and electrically isolated. For each motors, there should be some type of starters provided for starting the motor. In electrical side, when we are starting a motor, there is a chance of getting high amount of starting current at the starting period. So the primary function of the starter is to control or to reduce the starting current within the limit. And also it has the function of the controlling voltage, controlling frequency, and so on. There are so many functions over current control, earth fault control, but the primary function is to control or to limit the starting current at the period of starting. These are the electrical common specification about our RCP. I would like to concentrate on advanced reactors. I'm taking example for the AP1000. There are advanced type of RCP. The name is canned motor RCP. What is a canned motor RCP? It's eliminating the need for shaft seal. The shaft seal means, as we already said, when the RCP is operating, it's circulating forced flow of coolant. In other side, there is a component cooling water is also flowing through the RCP for cooling purpose. So there should be a seal to protect from these 2 types of flow of water. So when we are constructing the RCP, motor pump integral and encased within the pressure boundary So we can eliminate need for shaft seals. It's an advanced type of RCP that's used in the AP1000 reactors. In this also a vertical single speed centrifugal, but you can see in the picture it's inverted. In this, the impeller is at the top and the motor is at the top. It's the motor and impeller are encapsulated within a can. That's why it's called as a canned motor. In this AP1000, they are using two vertical single-stage centrifugal canned pumps per steam generator. Its flow capacity is about 4.97 meter cube per second. The voltage range is similar to that of normal RCP. It's varying from 6.97 kilovolt. As we already said, there are two types of frequency all over the world. One is 50 hertz and 60 hertz. It's depending upon the electrical supply available at the site. But normally we are using VFT, that is variable frequency drive. Sometimes it will call us triple VFT, that is variable voltage, variable frequency drive. It controls the starting of the RCP also. Here we can see that at low speed, up to 24% speed, at the starting time, the speed will be controlled at lower than 24%. After that, it will run through the normal speed. So the VFT provides that functions for this RCP. Normally, the RCP is connected in the cold leg of the primary loop. So it will avoid some mechanical issues like cavitation and so on. So in this, the canned motor, when we are starting, using the VFT, it will provide the starting mechanism. So during starting period, this will start with the low speed up to 24%. Whether it is 50 hertz or 60 hertz, the drive will provide the starting and operation of this RCP. This is an advanced type of reactor, canned motor RCPs. The next topic is about the instrumentation side of this RCP. Commonly, we are using RTD, that is an resistance temperature detector. It's a passive type of instrumentation device that detects the temperature by changing its resistance value. So its resistance value will change accordingly with the temperature. So we can measure the temperature using the varying resistance value by using another device. That's why it's called as a passive device. In here, we are using this RTD for measuring the stator winding temperature. There are three phase windings in stator. So 3 into 3, 9 sets of RTDs are used on the stator for stator winding temperature detection. Commonly, we are using silicon-based insulation, especially resins, for insulation purpose of this winding. So these RTDs are placing on the surface of the RTDs. And also, 5 numbers of vibration monitoring systems are also provided. These systems are using piezoelectric effect. That's when the vibration occurring in this system, this system will generate this electrical signals according to the vibration frequency. That's the piezoelectric effect. So there are 5 numbers of RCP vibration monitoring system. And last, they are providing 2 numbers of speed sensors for the function of speed monitoring system. These are the instrumentation part of the RCP. So when we are concluding, the RCP is a crucial part in the primary circuit of the reactor coolant. It connects in the cold leg of the primary loop. It provides the forced circulation of the coolant. It's a vertical single-stage centrifugal pump. Simply a squirrel cage induction motor. For safety, the supply should be physically separated and electrically isolated. So It's a there are many more details to deep dive in this topic, but for now, I'm concluding this presentation. If you have any doubts regarding this topic, please feel free to ask any questions on this topic. Thank you for watching my presentation. You can ask any questions on this topic. I'm eagerly waiting for your questions on this topic. Then we can explain more about the topic.
Thank you, Shabir. Guys, if you have any doubt, please.
Sure, can you please go to the next slide?
Is it?
Next one. Here, sorry, I couldn't catch what is canned motor RCPs and what is shaft seals, eliminating of shaft seal from the common type.
You can. It's a common type RCP. Here you can see there are seal housing, and also there are some provisions for providing the shaft seals, and also for accessing during maintenance periods, there is a provision as pool device. Using that, we can access the shaft seal evenly during the maintenance period. It's a disadvantage of the reactor coolant pump due to the shaft seal. There is a chance of maintenance due to the shaft seal. In this, there is no need of shaft seal because the impeller side, the pump side, and the motor side are encapsulated within a can. There is no separation in between the motor and the impeller. The whole parts are encapsulated in a can. There is no need of sealing these in between the shafts. Here, in normal case, the motor and impeller side are connected between a shaft, and in between that shaft, they are providing
Here,
seals
where is the propeller?
at the top. There is impeller. You can see my cursor.
Okay, yeah. That will be
here we can see here we can see there are suction nozzle.
Actually, your cursor is not visible.
Okay. Yeah.
Okay, fine. You can. I got it. You can proceed.
Oh, yes. There should be a suction nozzle and also
got it.
Yes.
Thanks.
If you have any doubts, you can ask. Otherwise, we can move on.
Salah Taslim, mechanical team, is there any further question related to
In the for loop reactor, so if one of any pump is damaged or not working, so how will we manage like the output of the reactor should maintain or something like that? So how will we manage like that kind of situation?
So Salah, in case of for loop, even though one or two RCP is not working, the reactor can easily operate during the normal operating period, as the normal operating period, because two numbers of RCP is enough for operating the reactor up to the full power capacity. But for the safety and for the efficient operation, we are providing 4 loops here. So if one of the RCP is under maintenance or it's code faulty, as I said, each and every RCP is physically separated, and it is situated in different within the partitions. There should be some type of concrete divisions, separations in between these RCPs. So normally, if there is any severe damage, we will troubleshoot the damage as much as the technicians possible without any reactor trip. I think if any clarifications, anyone can correct me. So without reactor trip, we can troubleshoot the reactor coolant pump, but it's better to shut down the reactor and take the maintenance because the primary loop is primary coolant is flowing through all the circuits. For the safety and the protection, it's better to take the maintenance after shutdowning the reactor. So if you want to take the maintenance, we normally shut down on the reactor. But we can operate the reactor without two RCP also not in working condition. Two RCPs are enough for generating full power output in case of the uh, for loop primary. Is it your asking?
Okay, sir. Thank you.
It's clear, right? If an RCP is in faulty condition, it can the heat generator inside the reactor core can be removed using two RCPs. That's what Shadir was explaining. But obviously, the next step it will be going to a reactor trip, and in order to remove the heat, two RCPs are now, and we will be obviously if there is an RCP faulty, the reactor will be shut down and going to be maintenance. Oh, guys, if there is any no further questions, we can move on to Vinay. Hi, if you have any question regarding the instrumentation part of the RCP.
No, Riaz, it's just RTD, right? No.
Yeah. Taking the temperature inside. Yeah. Okay, then Vinay, you can start your presentation. It's mute, Vinay.
Hello, everyone. So let's discuss about the plant electrical distribution system. Actually, we have different sources, transformers, and buses, and depending upon the specific designs. So let me share my screen. Let me know if you guys can see the screen here.
Yes.
So this is just a simplified SLD or actually the electrical system of a power plant is designed to provide reliable power sources which are physically and electrically isolated so that any single failure occurs in one supply will not affect the alternative one. So here we can see generally in electrical system consists of main power system and auxiliary power system. So you guys want to see my cursor here?
Yeah.
So the main power system consists of the main generator and the associated controls necessary to transmit the power to the offsite grid. So here, this is the main generator and it is using main transformer. We are stepping up and connecting to the turbine island bus bar. From there, we are transmitting it to offsite grid. So the transmission voltage is 400 kilovolt. Usually generating voltage is 25 kilovolts, so that is stepping up and transmitting with 400 kilovolt of power supply. And the auxiliary power system, which means it is made up of two sources of power. One is from this offsite grid, through this auxiliary transformer. Actually, this power is called the unit auxiliary power, and another one is through the reserve transformer from the another standalone offsite grid. So this is called the reserve power. Actually, it is designed for redundancy and to ensure the continuous operation in case any failure happen in this offsite, in this grid, uh, in this power system. So and the two sources of this auxiliary power are required to be independent, as we can see here, and similarly it is electrically isolated. And this power is transformed, this supply is transformed to the plant electrical distribution bus voltages by one or more system auxiliary transformers. Actually, here you can see from here, this unit auxiliary transformer, we are reduced the voltage, like the step down the voltage from 400 kV to 110 kV. Similarly, here 110 kV to 10 kV, and this one we will discuss, and so on. As per the requirements of each equipment, we are using multiple number of unit auxiliary transformers in this scheme in this power distribution system for the desired voltage. And yeah, for normal like we have safety and non-safety related drives in this nuclear power plant. So we are using normal power supply, which is from the offsite. This normal power supply using for these non-safety related drives because usually this emergency DG is considering for emergency power supply when in case failure of this offsite power supply or this main generator power supply. And we do have UPS power supply in case of these EDGs also. In case of these EDGs also, when there is a delay to start this emergency DG. So meantime, we are using this UPS to supply the safety related drives. And let me show you each scenario, like when the starting and the shutdown stage of the nuclear power plant, we are using the power from the offsite power supply. So you can see the red mark which I have marked in this SLD. So the power is taken from this 400 kilovolt offsite grid, and through this unit auxiliary transformer, we are achieving desired voltage for each bus required. And similarly, in the normal operating situation, the plant, this nuclear plant is generating the power, which is transmitting to this offsite power grid. Similarly, from this B1 bus bar, we are using the power for our station operations through this unit auxiliary transformers and remain as same as before we explained. Yeah, is it clear? This operation is clear?
Yes, guys, from mechanical and safety team, you can ask and instrumentation as well. If you have any doubt, please ask.
Okay. So let's consider when there is no offsite power supply, there is no offsite 400 kilovolt power supply is available and generator is not in the working condition. In that situation, we have standby power supply of 110 kV. We are using that 110 kV offsite grid to power our nuclear plant. So everything is so all other related power equipments are powering through this offsite grid. through using this reserve auxiliary transformer. Hope it is clear. So
Yeah,
these are
this
the
this offsite grid is it's like a generator or any.
it's
just
another
directly from the grid.
it's another power supply in the grid. From the grid, it is reaching to this power plant location. This is another isolated grid. This two grid doesn't have any connection each other. This is transmitting grid. This is another transmission grid from the connection from the main grid, another main. So these two are independent. Okay. Clarify. You are done.
Oh yeah, yes, thank you.
So let's look into our emergency power supply system. Actually, this emergency power supply system is a crucial safety feature. Is designed to ensure the continuous operation of essential systems in the event of loss of power and failure of the main generator. Like as we already mentioned, if we don't have any power supply from the outside grid and from the main generator, we have to rely on the emergency power supply system. Actually, this nuclear power plant must comply with strict regulations to ensure the redundancy and reliability of emergency power supply systems. As part of defense in depth, we have multiple layers of backup power are required to mitigate the common risk of common loss failures. Actually, the main purpose of this emergency power supply system is to supply to emergency consumers, as like the safety systems and instrumentation and control systems. Actually, these systems are vital for maintaining the safe shutdown in case of any event happened. So, for the safe shutdown, we need this system and or managing residual heat and preventing the release of radioactive materials. So, as we can see, the main component of this emergency supply system is the emergency diesel generator. Actually, it is considering as the primary backup for extended power outages. When we have the power losses, this is considering as the primary backup, like the emergency diesel generator. And this diesel generator is typically in each section has its own diesel generator. Like we can, like Shabir is mentioned, we have four. If we consider four RCPs are there, so we'll consider it as a 4 divisions. So each divisions we have own diesel generators, and these generators usually designed to start automatically when automatically after detecting a loss of power, and can supply the necessary electricity to keep the critical systems operational. So every critical systems are connected this with this bus bar 03 only. Okay. And when considering an emergency DG, we need to learn about load sequencing. So, when there is no power, there is no offsite power, we need to load these all the essential components to this EDG. So it starts supplying the power to critical loads in a predefined sequence to avoid the overloading the generator, and to prioritize the most essential system is known as so we need to prioritize the most essential systems in a sequence of connection, so which is called the load sequencing. So during startup, during startup of a diesel generator, we will ensure the main consumer, like the large electrical loads, which is not part of the critical system, will be temporarily cut off, and we will only feed to this like these all switches you can see my cursor. So this will be open, and it won't feed any other system which is not part of the essential power supply system. And the diesel generator load sequence outlines a step-by-step process of reconnecting the electrical loads. So the electrical loads such as the main heat sink injection pump. So these all are we are using for removal of decay heats, everything. And the low head safety injection pump. And similarly, chemical volume control system charging pump, emergency feed water pump, component cooling water system pump, essential service water system pump, emergency board injection system pump, and to the EDG. The sequence, so while we ensuring this sequence, the generator won't be overloaded. Like if we directly loading all these loads together, the generator will get overloaded suddenly. So if we following the sequence, it can handle the reconnection of systems in a controlled manner, and it will prevent the overloading and allows this DG to work in a stable operating condition. And we can see here we have low voltage with the voltage rating of 400 volt, 690 volt, similarly 24 volt and 220 volts. So 690 we are using a we are using the UPS. So this here is the UPS batteries, and these UPS and batteries are designed to provide immediate power for short duration during the power disruption. Usually, and up to 12 hours, we can provide the power. These systems ensure a continuous power supply to critical systems until the diesel generator can start and take over. So until this diesel generator starts, so these UPS and battery systems are supporting the critical components. And similarly, the main batteries and the severe accident batteries, which operate at 220 voltage, guarantee the availability of power to all necessary critical systems. So here we do have the control voltages, which is 220 volt. These are ensuring the availability of power to all necessary critical systems up to 12 hours of period. And there will be this 220 volt. Also, we are using a inverter. We will be invert this 220 volt DC to 400 volt AC, and we are ensuring the AC 400 volt AC system also will be remain operational. Sorry. So this is clear. Like, and we have 24 volt DC, which is using to power the instrumentation and control systems. And
during the emergency situation. Yeah.
Yes, exactly.
Yeah,
exactly.
yeah.
So usually these UPS and DG only will work in an emergency situation if there is an event happened. Like we can say case study example from Fukushima. There is actually what happened is due to the tsunami, the both offsite and the backup diesel generator has been disabled. Okay, so from there we have learned to enhance our flood protection for this emergency power system. So the EDG location where we are keeping an additional backup power sources, including portable generators, and improved redundancy and diversity in the power supply system. So there will be multiple number of DGs we will be using, and there will be portable DGs we will be using, and there will be diversify the power supply system. There will be multiple sections of these kind of arrangements. It's not only single. See, here I left it, here I left it. So these are part of redundancy. As we already in our previous classes we have discussed. I hope everybody will be remember the same. So in a nuclear power plant, as we concluded, in a nuclear power plant, the emergency power supply system in a loss of AC scenario is vital component of the plant safety infrastructure. And by designing the redundant and diverse and reliable power system, the nuclear power plant can ensure continuous operation of safety critical system during emergencies and preventing catastrophic failures and protecting the public health and safety. So this is just an overall view of the power system. And while even the unavailability of entire power system station will be close to the station blackout scenario, and that's a different session we can discuss on going forward. Thank you. Please let me know if there is any queries on this section, what I have explained till now.
Thank you, Vinayakan. Thank you for a wonderful session. If you have any doubts, please shoot at Vinayakan.
Yeah, Vinayak,
Right.
if the reason it happens, this both means if there is power supply cutoff, then both EDG and UPS will work same together, or if EDG is not working, then only UPS will work like that.
So this UPS, generally the UPS will be act when there is no power from the offsite, and EDG will take bit of time to start and getting in the normal operation. So the meantime, this UPS will be helps to be remain operational for the critical components, and this battery backups is helping when there is absence of DG also, like Fukushima. There is DG also disabled in this tsunami. So I don't know about what about their UPS backup, but after that after this event, this design mainly the reactor design is focused mainly in this diversity of these power supply systems, like these backup power supply systems, and the redundancy to ensure each mechanical component, critical mechanical components in the system, like the INC systems and other equipment system which remains to operation required to be operational until the nuclear power plant to cool down.
Okay, Vinayak, thanks.
Okay. Is there any further questions from mechanical and instrumentation team? As well as say, do you have any further question related to electrical system? Okay. So, thank you, Vinayakan. Then we will move on to Suman, the safety team.
Yeah.
And
So
we will be discussing with safety.
share. So let me.
Yeah.
And everyone can see the.
Yes.
So the today, as we were talking about multiple time, or we have been talking about nuclear system safety, and today my topic is going to cover about HSC, the health and safety management at nuclear power plant construction, because we are in the future there will be many new build projects, and we don't know where we will be working. And it is also quite interesting topic, and it is also important to have a little understanding about the HSC aspect of the projects. So this presentation focuses on safety compliance, the protection of the workers, safety awareness during the nuclear project. The key objectives of HSC management. Usually, the projects we call it HSC plan or HSC management plan. So there are many uh, uh, operator or a project consultant or whoever work in the projects have to have a project HSC plan. One of the reason is to compliance with the local regulatory requirements, and the second one is to minimize impact, and third one is to promote health and safety and create awareness. So this will be a very quick presentation. Hello, can everyone hear? I don't see you up on the screen. Yeah. Okay. So the first part is to give a little bit understanding about the regulatory requirement. So in different countries, different states have their own regulatory. Safety Work Act in 1974, which say the employer is responsible for employees' health, safety, and well-being at workplace. So the employer is responsible for the workers' health and safety. So there are standards, there are regulations to protect the workers, the people, so the appearance safety standards. So there are follow local and international safety regulations to ensure project safety. So there are as per the international safety standards we studied related to systems, nuclear power plant systems. But as a construction project point of view, HSC management is another aspect of the health and safety. So environmental protection is another requirement. So the measures to comply with environmental law and safeguarding the nature. In third world countries, in many countries, the environment aspect is not considered much. So in different parts of the world, the environmental aspect is key part to consider. And the nuclear safety regulations, we studied more about this in but So the HSC is, when it comes to HSC during the construction project, the